Hi guys, welcome to our fifth video in chapter 14. This video is going to concern gas stoichiometry. So all of the things that we have talked about thus far in our chapter 14 can be combined with what we learned about stoichiometry to make useful predictions and conclusions about chemical reactions and how much matter is going to be involved in those chemical reactions. So let's look at one condition where we could use our idea or our understandings of gases and our idea of stoichiometry to produce some useful information. So the easiest way to think about this is to start by considering calculations that only ask you to consider volume, right? I'm going to actually add a note here, volume of a gas, right? So we are, of course, dealing with gases. We will deal with solutions and liquid volumes later, if we haven't already talked about them. So when you're dealing with the ideal gas law, just make sure you actually have a gas and not a liquid. So recall Avogadro's principle, and I have it underlined because it's going to make our job very easy. Avogadro's principle says that equal volumes of gases at the same temperature and pressure have the same number of particles. And the convenient thing about many chemical reactions is that if we are combining two gases, it could be very easy to get them at the same temperature and pressure because they're probably going to be mixed in the same container. All right. So this assumption of Avogadro's principle is mostly true for our chemical reactions. And here I put a star by this and I highlighted it because this is what makes our lives very easy. If we apply the Avogadro's principle, we can conclude that not only do the coefficients in a balanced chemical equation represent the amounts of moles, but because of the fact that those gases have the same number of particles, it can also represent relative volumes. So that means that we don't necessarily need to go all the way through most of our stoichiometry. We can, in fact, draw useful conclusions just knowing that if I have a balanced chemical equation for the combustion of methane gas, if I know that 1 mole or 1 molecule, all right, of methane reacts with 2 molecules or 2 moles of oxygen, and it forms 1 mole of CO2, carbon dioxide, and 2 moles of water, respectively. I know that to be my chemical equation in terms of moles. Well, because these gases are going to take up they're going to have the same number of particles per volume, I can also say that if I take 1 volume unit of methane and combine it with 2 volume units of oxygen, I will form 1 volume unit of carbon dioxide and 2 volumes of water. Notice that I didn't say specifically this had to be in liters or gallons or anything. In fact, it is not specific to a unit of volume. You can use any unit of volume you want for these types of questions of calculations. And this, again, makes our lives pretty easy. So let's, not pretty easy, easier than they would otherwise be. So let's look at an example. In this example, the question says, what volume of oxygen gas is needed to complete the combustion of 4 liters of propane gas, C3H8, assume constant pressure and temperature. Okay, so I'm going to make some highlights, right? What volume, we're looking for V, of oxygen gas is needed to complete the combustion of 4 liters of propane gas at, there's your formula. Okay, so let me grab this. Now, one thing to remember is this is, of course, a chemical reaction, which tells me, I'm going to say chem reaction, which tells me that this is going to be a stoichiometry problem. And so if I have a stoichiometry problem, the very first thing that I always need is a balanced reaction. Okay, so I'm going to start by drawing that balanced chemical reaction, and then I'm going to see if I can determine how much oxygen I will, in fact, need. So if I have a combustion reaction of propane, I'm going to, of course, combine my C3H8 plus some amount of oxygen. And a combustion reaction is going to form carbon dioxide, CO2, and H2O. Okay, so for the purposes of moving forward in chemistry, we are going to go back and actually add our states to these chemicals. This is a gas, this is a gas, it's a gas, and our water is a gas. So all of these things are gases. Now, if I balance my chemical equation here, I'm going to get the coefficients of 1, 5, 3, and 4. 1, 5, 3, 4. Okay, so balanced chemical equation, all looks good. And then I also know that all of these things are gases, which tells me, and I'll write this out, right? So because all are gases, well, it doesn't have to be that they're all gases, right? Our species, the species we are concerned about with our gases, right? And that is key. We know they're gases. We can use our idea that molar volumes can be compared here. So we can use that idea. Well, if I know that I start with 4 liters of 4.00 liters of my propane gas, C3H8, well, I can do a quick unit conversion. I said in my balanced equation, I had 1 mole of C3H8, or again, we could say 1 mole, or we could say 1 volume. In this case, I'm going to say 1 liter. And notice if I have 1 liter of C3H8, that is going to combine with 5 mole, 1 mole of this would combine with 5 moles of oxygen, or 5 liters of oxygen. So 5LO2. And so with my units here, I can cancel out liters of C3H8, and I'm going to be left with oxygen, which is the quantity and species that I'm searching for. And so 4.00 times 5 over 1 is going to get me an answer of 20.0 liters of O2. And that is the amount of oxygen gas that would be required to combine with 4 liters of propane. Interesting. Bad news if you are competing with propane to use this oxygen, because you can see a little bit of propane takes a lot of oxygen. And, we need oxygen to maintain homeostasis. Anyway, so good stuff. Hopefully you see in this equation that our concept of using volume ratios can make this much, much easier. Okay, let's look at making this a little bit more complicated, right? So calculations that involve both volume and mass. If we combine our stoichiometry skills, like real stoichiometry skills, the gram to mole to gram, with the combined gas law, or sorry, with our ideal gas law, we can do some very useful calculations. And I want you to remember, of course, that your temperature does have to be in Kelvin because we are talking about the kinetic energy of particles. And here's the example I'd like to go through. Volume to mass problems, right? It says ammonia is synthesized from hydrogen and nitrogen gases according to this following equation. It is balanced. I can see coefficients here. This is I can't overstate the importance of this chemical reaction. This, if you want like an interesting chemical reaction to look up, this is one. They say that this chemical reaction alone possibly prolonged World War I by up to 6 months. Just the existence of this reaction. But I'll let you look that up on your own if you're interested. Anyway, so the question tells us we've got 5.00 liters of nitrogen gas. I'm going to highlight that, right? That seems important. 5 liters of nitrogen is going to reacts completely by this reaction at a constant pressure and temperature of 3 atmospheres and 298 Kelvin. How many grams of ammonia are produced? So let's start, of course, by listing out all of the things that the question gives us. First thing that I see is that the question gives us our initial volume of nitrogen. So I'm going to say VN2 is 5.00 liters. I'm going to just denote that that is nitrogen gas because I see I have 3 species, each are in the gas phase. So I want to make sure I know exactly which chemical is taking up those 5 liters. I also know my pressure to be 3.00 atm and my temperature to be 298 Kelvin. It's already in Kelvin. Cool stuff. And I know that my mass of NH3, my mass of ammonia, MNH3, that is what I want to find, right? That's what it says, how many grams of ammonia are produced. And so you can see why I'm being very careful to label some of these properties. I have the volume of nitrogen, and I'm searching for the mass of ammonia. So let's begin solving for this. If I look up in my balanced chemical equation, I can see that for every 1 nitrogen, so for every 1 liter or 1 volume of nitrogen, I'll say volume of N2, right? I have that here, is going to create 2 volumes of 2 volumes of ammonia, NH3, okay? So if I start with 5.00 liters of NH3, sorry, N2, right? Not NH3, N2, and I multiply it by my conversion factor here. Let's see, I can cancel liters of N2 out. I'm sorry, hold up. My N2 cancels and my volumes unit cancels, and I'm left with liters of NH3. Good stuff, which is what I want. And this, of course, 5 times 2 is going to give me 10.0 liters of NH3 gas produced. So that's all good stuff. Now, I need to determine what is the actual number of, if this is the volume of my ammonia produced, what is the actual mass? Okay, so in order to solve for mass, I'm going to use the ideal gas law, right? So I'm going to actually draw a line here and separate this into kind of 2 parts. This was gas stuff, gas plus stoich. And then now down here, we're just going to be dealing with gas stuff, gases, right? So we know we have 10.0 liters of our NH3. And we are going to, of course, start with drawing our ideal gas law, PV equals nRT. And we might be saying to ourselves, well, if I want to find the mass of ammonia in this equation, the thing that is going to actually allow me to solve and calculate mass is N. So I'm going to solve for N. In order to do that, I'm going to divide RT over, divide up my RT, cancels out there. And this tells me that N equals PV over RT. And so now I can just plug and chug in order to find moles. Okay, so let me give myself a little more space. Cool, so we said N equals PV over RT. P was 3.00 atmospheres. ATM. We had 10.0 liters of NH3. That's our liters. For this question, I have atmospheres in my pressure unit. So if I think about which ideal gas law constant I'm going to use, I am going to use the one that has atmospheres. So liters times atmospheres per mole per Kelvin. That's 0.08206. Okay, so I'm going to plug that in as my R constant, 0.08206 liters, atmospheres over mole Kelvin. That's an L, not a C. And then finally, I am, of course, going to add my temperature, 298 Kelvin. And so the beauty of stoichiometry is apparent. Again, atmospheres cancels, liters cancels, Kelvins cancel. I'm left with only mole. It is in the denominator of my denominator. So again, that is going to keep change, flip its way up to the top, and I'll be left with mole. And if I math this thing correctly, I should get 1.23 mole of NH3. And so now, if we are, of course, right, we're at mole, and we want to get to mass of ammonia, so let's multiply our moles by the molar mass in order to figure out how many grams we have. So 1.23 mole of NH3 times 1 mole, our molar mass being 17.04 grams of NH3 per every 1 mole of NH3. And canceling out my units, moles of NH3 cancels. I'm left with grams of NH3, which is exactly what I'm looking for. And if I do this math, I will get 21.0 grams of NH3. And so you can see if we combine our stoichiometry with our gas laws, not only can we do some very powerful and flexible calculations, but we can start with a certain given volume of nitrogen gas, and we could predict what mass of ammonia could be produced from a very important chemical reaction. All right, guys, that's all I have for this video. Thank you for listening, and I'll see you in the next one.